First of all, I'd just like to acknowledge Cam Knoll, who taught me a lot of what I know many, many years ago now. So I attended his workshop a long time ago, and have now built a fairly good career based on that work. So just a shout out to Cam down at MIPS. Um, Little ad for us. So we are the bioimaging platform. We have variety of equipment in optical EM and flow cytometry, as well as histology. I haven't updated the slide, but we now have histology platform. So if you need any assistance, then please, even if it's just a bit of advice, then please reach out to us. We are on Twitter. I know Twitter is a bit of a wasteland at the moment. We're also on Blue Sky, but we are on Twitter if you want to follow us for all of the updates that we give. I typically run these workshops via cinema rules. Essentially, keep your phone screens and microphone cameras quiet so you don't distract the other patrons. If you do need to ask a quick question, please use the chat feature. I'll be turning off my camera in a minute, and I'll answer them during the workshop. If it's a bigger question that's going to require a fair amount of work, an explanation, then please feel free to email me either during the workshop or afterwards, and I'll get back to you as soon as I can. This is the proposed timetable for the workshops this year. So today we're doing part 1. I used to do these as 3 to 4 hour workshops, but it's a bit much. And just for sort of to make it a little bit more comfortable, I've broken it up even further into smaller chunks. So part 1 will be today, and that was supposed to be March 6th was the original day. I'll change that time. We'll be doing part 2 of this, which is expanding on the analysis, which will be in May. June, July, we'll do a QPath workshop, which is a histology AI analysis program, which is a really good program to use, especially if you're doing slide scanning or any histology analysis. So H&Es all the way up to immunohistochemistry. In August, we'll be doing part 3, which will be advanced FIJI for analysis. I say advanced, but it's not crazy hard. It's just more time series analysis and things like that. Colocalization will be part of that. In September or October, I'll be continuing on QPath to the more advanced features. And finally, in November, I'll be doing a fundamentals of script writing. So everything that you can do in FIJI, you can also write scripts, programming plugins that you can then use to automate your work so that you push a button and it does all of the work that you were doing by pushing dozens, if not hundreds of buttons. So that will be later on in the year. So the basic outline for this will be, of course, just a quick introduction to what FIJI and ImageJ are. The basic functions, a bit about image manipulation. The 10-minute break was when we did this for 3 or 4 hours, so we probably won't have a break with this. We'll just sort of rock on through the 2 hours. Then we'll look at the multidimensional imaging, very basic analysis. And then if time, we'll have an overtime discussion where you can ask any questions that you need. So the aims of this workshop is to learn, of course, the basic functionality of ImageJ. So this is meant for somebody who has either never used FIJI or ImageJ before or has a basic knowledge. So we'll be expanding and creating a foundation that we can then build on in later workshops. And just to get an idea of the vast amount of processing and analysis capabilities that we can use in the software, which you can then use to design your experimental analysis accordingly. Who wants to be let in? Started by you. Michaela. Okay. So the workshop and the examples that we're going to cover are very broad. So they sort of show the basic functionality, and as we go on through the different parts through the year, you'll see more and more expanded functionality. It's not limited to those examples. FIJI is a massive software. There is people are writing new plugins for it all the times. The plugins that you find within FIJI are only the basic ones. You can download new ones for free that are available. Sometimes you'll be reading a paper. We created XYZ plugin, or we used XYZ plugin for this, which you can then, if you want to replicate the work, you can actually go out and download and install that and use it. So it's not just for the functionality that we're looking at. It's pretty much whatever you want to do. FIJI can typically do it quite well. So I'm going to turn off my camera. So part one, introduction to FIJI and ImageJ. So what is ImageJ? So ImageJ, J stands for the programming language Java, is public domain Java-based image processing program, first developed in the NIH. Now, because it's public domain, it is available to for anyone to use free forever. So whenever if you need to use ImageJ at any point, it's always going to be there. Because it's written in Java, it's available across all of the operating systems in 32-bit and 64-bit. I don't even know if I don't even think they make 32-bit computers anymore. It's distributed in open source, so anyone can download the source code and change it. They can create scripts and plugins within the program to aid in their analysis. And as I said before, the scripts and plugins are often cited in papers, or made available by the creators. So you can download and run it within the software for free, and it's free forever. You can literally just you will because it's publicly funded. It is available for any researcher to download anytime, whenever they want to. So what is FIJI then? So FIJI is an acronym which stands for FIJI is just ImageJ, and that's what it is. It is just ImageJ. However, it is a pre-packaged version of ImageJ that has a whole bunch of extra functionality. It's a different, like Linux builds. There's different Linux flavors all over the place for all sorts of different functionality. FIJI is the ImageJ expanded version. I honestly have not used bog standard off-the-shelf ImageJ for well over a decade, because FIJI has everything and anything that I could really want, whereas ImageJ is a basic image analysis software that you then have to update with all the plugins that you want to use, whereas FIJI has a lot of really good functionality already built into it, and it updates itself every time you open it. It will ask you if you want to update. So running FIJI, so FIJI can be downloaded for free from the FIJI website, fiji.sc. Now, on a PC, you don't actually have to install it. You literally just uncompress the zip file that you download, and then you can run it from either your desktop, a USB drive, or even from a server. So it can be run just as a little program, and it's very portable. So you don't have to go through the installation. You expand it, put it somewhere on your computer, and just run it. Mac's a little bit different. You need to download the compressed file. If you double click on it, it'll come up with this page here, where it just tells you to drop FIJI into the applications folder, and then it should be available to use as a program. There is, like a lot of things, there is a wiki for this, which is just imagej.net. It is a wiki that allows you to look at any plugins, a lot of plugins that are available. Like obviously there are some obscure ones which may not be in there, but a lot of the functionality that is especially available in FIJI, you can look up how to actually use it within the ImageJ wiki. So it's a good resource to have. Assigning memories and threads. So when your computer has a certain amount of RAM, and each program needs that RAM to be able to run. Now, what you can do is go into the edit. Now, I should have said at the start, a lot of the sort of the examples that I'll be going over, you're more than welcome. You should have received the shared folder that I sent to you, and there are a lot of bits and pieces in there which we'll be running through today. Or you can literally just watch along with what I'm doing. And then I will supply the PowerPoint that you'll be seeing, as well as the recording, which is available through Teams. So you can do a lot of this in your own time afterwards. So FIJI allows you to actually assign the amount of RAM that you want to use. So if you have a lot of RAM, you can assign a lot of RAM to FIJI for it to use. And you do that via Edit, Options, and Memory and Threads. Now, FIJI will automatically assign itself about 70% of your total RAM and will have access to all of your CPU threads. So you can change the maximum amount of memory. So you can give it 100% if you really want to, but you do need to remember that your other background processes, for example, Windows, needs RAM to be able to run. So just be aware not to give it too much, or you may actually find Windows running itself into the ground because it hasn't got enough RAM. The garbage collector. So as ImageJ is running, and I'll pull up ImageJ right now. So here's ImageJ. So this is just a little window that runs. So ImageJ is just a little window that runs like that. And down the bottom in the status bar, it will allow you to double click on it, and it will clear whatever images are kept in the memory. So these are images that you may have opened and then closed, but because of the way that ImageJ runs, it keeps them as a copy within the RAM, just so it can use it again. So it's a good idea to every now and again just double click on this little function under the memory when you're setting. That should already be checked. If I go in here, Edit, Options, Memory and Threads, it should already be selected as part of just the general setup. So yeah, if you notice ImageJ becoming sluggish, just double click on it and it will clear up the memory, and you can actually see I have 31 megabytes of my 12 gigabytes of RAM available. Updating FIJI. Every time you open FIJI, you'll get this little window which will say, do you want to start the updater now? You can say, no, not right now. You can also say, no, never do that, but I don't recommend you do that. Maybe skip it a couple of times if you're it only takes a couple of minutes to download the latest update and install, then makes you shut it down and then start up again. So if you are pressed for time, then maybe skip it once or twice, but it's a good idea to run the updater as many times as you can before you start, because things change daily. Literally, there is a daily build, sometimes multiple daily builds, depending on updates, bugs that they've fixed, and it's a good idea to run the updater by clicking OK. It will download the latest version, and then you click Update Changes, and it will update it, and then say you need to shut this down before everything takes effect. So it's a good idea to do that as well. If you want to, you can run it manually. If I find where FIJI has gone. So here's the little window. So you've got remind me later, never, or yes, please. And I do recommend you running yes, please. But you can run it manually by going into Windows, Help, I should say, and Update, and it will bring up the updated window to allow you to then download everything and run that. Plugins, as I said before, there are a lot of plugins already in FIJI. However, you can add new ones for different functionalities that you would like to. For PC, it's very easy. You just go into the folder where ImageJ, the one that you've uncompressed that you're running FIJI from, there's the application itself, so you would double click on that to run it. However, in that folder also is a folder marked plugins. So anytime you download a new plugin, you would just drag, and sometimes you need to decompress it from a zip file, but just literally just drop it into the plugins file, restart FIJI, and then the new macro will appear in the plugins menu. So if you bring in FIJI and click on plugins, you'll get this entire list of plugins which are already in there, and whatever plugin that you have added, it should then appear in that list. There is another way of doing this. Some plugins are actually installed on the FIJI server, and there are usually instructions that on any websites that promote these plugins. Essentially, it tells you to tick us to go into the if you run your update, and under the file, just downloading. Plugins. Eventually we'll finish. So then you'll get this window, and then under Manage Update Sites, you'll get a whole lot of sites which are available for plugins. So all you would do is you would activate a certain plugin, click Apply and Close, and then click Apply Changes, and then that will add that plugin. Now, the reason why these aren't already automatically ticked is it would just make your plugin folder completely unmanageable and just be cluttered up with hundreds of different plugins. So we don't typically do that. So I'm just going to click Apply Changes, and it's going to update my download the update and update that for me. Basic functions. Basic functions in FIJI. So opening images is very, very simple. So FIJI will open virtually any microscopy format using the Bioformats plugin, which is a group of people who every time there is a new microscopy format, they will write essentially a decoder, which will look at the image and allow FIJI to then open it. Update successfully, please restart image J. Okay. So pretty much all you should need to do is when you have your when you have your data, and I will just go into, so I'm just going to go into the OneDrive folder that we created, and you should have FIJI workshops. No, that's not right. Where did I put it? FIJI workshop resources, sorry. Part 1. So let's just grab an image, any image, so 3-channel fluorescence. It doesn't have to be anything specific, but all you would do is grab an image and drag and drop, and then it will open immediately. And this is just a simple TIFF, but any image should be able to be opened up essentially through that functionality. These are all the typical microscopy formats that we use. And FIJI is updated regularly to ensure that new formats are accessible. You can just go into, if you wanted to, open and then look for a file and then open it that way, but it's just easier just to drag and drop. Open recent images. If you have closed an image that you want to reuse, just simply go into File, Open Recent, and grab that image again. And I think it's in the background somewhere. There we go. Open Recent. There we go. It's disappeared. That again. Okay, cytoskeleton green. And open recent, and oh, that's weird. Bug in the system. That image, just wondering if it's, oh, it's disappeared. That's weird. Reuse image isn't working for whatever reason. I wonder if that's a bug in the system. Anyway, normally that works. I'm not sure why, for whatever reason, it's not working. Anyway, but it should work. Sample images, which we will be using in the later part of this course. So sample images are images that are on the FIJI server that you can download to use for whatever purposes. So the image that we'll be using a bit in here, so if I go to open samples, image that I like to use is the Flybrain image. So if I click on Flybrain, it will download it from the server and it'll give you this image of a Flybrain. So if I go through, it's a confocal stack, and you can see throughout the image, and then you can use that for whatever purposes you want. But there are all sorts of sample images. So if you want to have a play around with something and you don't have a specific image that you want to use, then you may want to download one of these practice images. So that's just some embryos by the look of it. Saving images, save as, file, save as. You can save as the general imaging functions, TIFFs and JPEGs and bitmaps and things like that, or you can save as more specific. I can't say I've ever used any of these specific formats. Most of the time we would just use a TIFF is usually the way to go, or PNG. They're both uncompressed images. So you've got a lot of options there. Image information. So whenever we open up an image, we've got some information that we can get from FIJI. So let's open up an image. So here you can see within the image itself, you can see that this image is 1600 by 1200 pixels. It's 16-bit and it's 3.7 megabytes. On the ImageJ status bar at the top, wherever I move my icon, it'll actually tell me the X and Y position of where I am. It'll also give me an intensity value. Now, this image isn't calibrated, which means it doesn't have a scale. So if I actually go find an image with a scale, which I'm pretty sure I have one, the Flybrain, of course. So the Flybrain is actually calibrated. So you can actually see that this image is actually 684.93 by 684.93 microns squared, whereas the image that we had before had not been calibrated. It's just literally showing me the pixels. So we get into calibration a little bit later, but that will give you a lot more information if you need it at a glance. If you want more image information regarding the metadata, now metadata is image information that is stored essentially invisibly within an image. Now, this might be as simple as scale information, so how big a pixel actually is. It might actually give you information regarding how the image was captured, so confocal settings. So if I bring this up and go into image show info, it'll actually tell me a bit about how this image, a bit about what's going on with this image. It's very basic because it's a saved version of the original raw data, but it tells me how big it is. It'll show me where it currently is saved. The date that it was actually, I've been using this image since 2016, the date it was actually created. I captured this on a spot camera way back when, so it actually has a bunch of information. But with say for a raw confocal image, it actually might have laser settings. I used a 10% laser power. So it depends on the type of image and how it was actually captured, what data is actually in there. So you can actually see that separately. Image navigation. So navigating through the image is very important, of course, and we can use the basic functionality of the magnifying glass and the little hand tool. So selecting the magnifying glass just there, I can use I can click on part of the image, left click, right click will zoom in and out. I can also use the plus and minus buttons on the keyboard if I want to. I think, what is it, page up and page down? No, there's another function that I can use, which escapes me at the moment. Have I got it there? Up-down keys. So if I use the up-down keys as well, then I can also do that as well. To change the image position, so if I zoom in, you can then use the hand tool to move around. This little map up in the corner tells you whereabouts in the image you actually are. You can't click within that to get to a specific place, but you can sort of use that as a navigational tool. Pressing the space bar will also select the drag tool as long as it's pressed. So if you bring up image J, so if I have the magnifying tool pressed, I can hold down the space bar, and that will convert that to the hand tool. And then when I let go, it goes back to the magnifying tool. And then if I hold down space again, it turns back into my drag tool. That's the navigator I was just talking about there. Synchronize windows is a good tool to have. So if I have two images of the same region but different channels, so I'm going to open up within my 3-channel fluorescent folder. I'm going to open up the cytoskeleton green and the mitochondrial red image. Now these are 2 channels, a red, even though it's black and white, it's a red and a green channel, the mitochondria and the cytoskeleton of the same cells. So what I can do is I can, if I want to synchronize these windows, and by that I mean I can zoom in and navigate in both images at the same time. I would go to Analyze, Tools, and Synchronize Windows. This window will pop up, and it's got the 2 images that I've got open, and it syncs these functions. So your cursor, your channels, your coordinates, your Z slices, if you've got a Z stack, your time frames, if you've got a time series, and image scaling, the images remain the same scale. And then if I click Synchronize All, so now if I zoom into one spot and you see the little red arrow, it will actually synchronize to that identical cell. So I can go to identical cells, and so you can see there's the nuclei in that, and there's the nuclei in there. So you can actually see in both images and then I can drag around and have a look at the identical cells. To unsynchronize, you just click unsynchronize, and then it just functions as a single image navigation. Duplicating the image. Duplicating the image is quite handy if you are doing any modifications. So there's a few ways of doing this. You can either, if I bring up image J again, you can either go select the image you want to duplicate, go to image and then duplicate. You can also click Control-Shift-D. So if I click Control-Shift-D, it will ask me to give it a name, and I will just go working copy red and click OK. And then I get an identical image, not at the same zoom, but if I zoom out on both of them, they should be identical. You can also, if you want to, right click and select duplicate. They all do the same thing. And then you give the duplicate a name so you can tell the difference between the 2 of them. So that way you can modify one image, and if you make a mistake, you can close that one, go back to the original image, and start again without having to reopen the image. Or if you want to use the duplicate image as a mask or something to then process the other image, that's a good tool as well. And I often put those in scripts that I write, just so I've got that original image still there. Renaming an image, very simply, you can either go to image rename, you can also go to right click and rename, and you can give it a new name, and click OK, and then it's called the new name. Regions of interests, also known as ROIs. These are very handy tools, mostly used for isolating part of the image, either for measurement or manipulation. So on the ROI, on the main bar, you've got your ROIs across here. You've got square, circle, polygon, freehand, lines, angles, and multi-points. Now, under each one, if you right-click on any of them with a little arrow there, it gives you a bunch of different options. So if I want, instead of a rectangle, square, I can use a rounded rectangle, a rotated rectangle. On the circle, I can use ovals, ellipses, etc. So you've got a whole bunch of different tools. So what I'm going to do is I'm going to open up the ROI test, this little weird shape, just to show you what's going on. So easy, I can select a square and I can isolate the square. Now here, if I wanted to, if I just left that like that and click delete, it would delete that part of the image. If I clicked Control Z, it will undo. Now, the undo for this function for FIJI can be a bit spotty. Most functions can be undone, but you can only go back one step. If you do 2 mistakes and you try to go back, you can't do it. So it's 1 mistake and that's it. With the circle, do the circle. Now, the circle's a bit weird because it's not a perfect circle by default. Wherever you drag it, it's kind of an ellipse. So what you can do is use key combinations. So if you hold Shift on the keyboard, you can get a perfect circle, which extends out in all points identically. Now, that's not a really good sort of function if I want to do this. I'd have to kind of go in this corner and drag it perfectly. If you did Control, if you hold down Control or Command on Mac in the center, it actually extends from the center outwards rather than the corner. Then if you did Control and Shift, it will do a perfect circle from the center like that. And then you can move it around if you want to reposition it. We have the polygon. So if we want to do a triangle, we can do click, click, click. And then if you click back to the original point, now you've got your perfect perfect triangle. Freehand tool, if you want to attempt to freehand around a weird section or whatever, you can do that. And then you've got your section. If you're doing counting, for example, you've got the multi-point function, so I can use that to count. You see a little number will appear with each of those to keep count for you. I think it's Control A. If you hold down Control A, it will get rid of everything. If you try to delete, if you try to click delete, it doesn't let you. But yeah, if you hold down Control A, it gets rid of all of the sections. Now you will notice that when I draw a new object, the other one disappears. We'll talk about the ROI manager for storing that in a bit. But yeah, just be aware that if you don't store the ROIs, the previous one will disappear. And then if you want to, you can also just click off it just to get rid of it. Okay, so we're going to talk about pixels because we're dealing with digital imaging and pixels are very, very important. So what is a pixel? Now, pixel is shorthand for picture element, and it's the smallest element which makes up a digital image, and it contains brightness information, not necessarily color information, but brightness information. And every fluorescent digital image that you've ever seen in a publication is actually black and white. It's been captured in black and white and falsely colored. And it's made up of multiple channels, which gives you the red, green, and blue. So we'll talk about that a little bit more. Now, the pixels are, of course, small squares. Circular or polygon-shaped pixels would be inefficient, especially for digital displays. So we always create pixels as squares. Now, generally, the more pixels you have, the higher the detail. The more pixels and the smaller the pixels, the higher the detail of the overall image. In general, to a point. You can't create resolution from nothing. And there is a point where adding more pixels actually doesn't actually help anymore. So pixels have 2 dimensions and they're represented with a physical X and Y. So you've got X across and Y. Now, by definition, a pixel's X and Y are identical by just because. Now, obviously, every single pixel in a display is not 100% identical down to the picometer or nanometer or even micrometer. But for all intents and purposes, we just assume that they are identical in both the X and Y. Adding a third dimension depth adds a third, it creates a 3D pixel, which is known as a voxel or volume pixel element. Now, these occur when instead of doing a single two-dimensional image, we do three-dimensional Z stacks with a confocal. So you actually get a depth between the first frame and the second frame, and that's usually what your Z stack depth is. And every digital image is made up of pixels because it has to be. So if you zoom into any image close enough, you'll actually see that they're made up of small squares. And each one of these squares contains brightness information regarding a specific color channel. And then multiple color channels on top of each other creates usually an RGB, red, green, blue image, or whatever sort of, or even cyan, blue, cyan, yellow, magenta, depending what color space you're working in. But typically in fluorescent microscopy, we typically work in the RGB color space. So as part of the pixel, using pixel information, we need to know, if we're doing any measurement, we need to know what the size of every single pixel is in order to create measurements. Now, that usually comes down to the addition of a scale bar. So if the image is not correctly calibrated, and we were looking at the calibration information before, so you see that the image information is here. It knows exactly, to get the frame size, how big that image is, it needs to know how big every single pixel. So if you divided the total frame size, so 684, by the number of pixels across that, it would actually give you the exact size of each and every pixel, which is the basic number we need in order for calibration. So what we're going to do now is we're going to look at scales and how to determine the scale of an image, and if there is no scale, how to actually add one. So you can go into any image within FIJI, an image up. So let's grab the, go into samples, and let's download the FlyBrain again. And we can automatically see that the FlyBrain is calibrated. Now, if you go into the properties, instead of show info, if you go into properties, it gives you more of a succinct display of the information which is going on. All of this information will be available in the show info tab, but it's just in an editable form here. So from here in the properties, I can see that this has one channel. Now, technically this has two channels, a red and a green, but it has been compressed down into RGB instead of specific channels. And we'll talk about channels a bit later, but this is essentially an RGB image. There are 57 Z slices in this image. So if I click cancel, it allows me to then cycle through those. There is only one time point here, so we only have one time with the time point here. If you take a series of images over time, you would get multiple time frames here. And then we get to the important part, the pixel width. So every single pixel in this image is 2.6755 microns across by 2.6755 down. Now, the voxel depth, the distance between each Z stack, is almost 4 microns. So they've obviously, when they've done the Z stack, they've set their Z stacks to almost 4 microns. Now, this gives us the voxel information. Now, if you have an image which is not scaled, you can pretty much automatically tell. So if I open up the cytoskeleton green and I go to, you can always tell just by looking at that. But if I go to image and properties, you can tell because all of the pixel width, height, and depth information are all 1. That's the number one obvious sign that the image is not calibrated. First of all, it'd be almost impossible unless you did it specifically to make every single pixel width exactly 1. But the voxel depth is usually, just because of the way microscopy works, the voxel depth is always about 2 to 3 times larger than the X and Y pixel because of the resolution of the system. It's not as good in the depth resolution as it is in the X and Y. So typically if this was true, you'd assume that the voxel depth was 1 micron, or was about 2.5 to 3 microns. So if that is the case, then we would need to do something about that and recalibrate it. Also, the unit of length is pixel rather than micron. So that's obviously that there's something gone wrong. So what we can do is try and calibrate an uncalibrated image. Now, once the image is taken, it's very hard to actually calibrate it unless a scale bar has been added automatically by the system. If the scale bar hasn't been automatically added by the system, you will need to add it yourself, and you can do that via a stage micrometer. So a stage micrometer is literally just a ruler. It's a very, very fine ruler. This distance here is 1 millimeter, which has been broken up into 100 micron sections, and each one of those 100 micron sections have been broken up into 10 micron sections. So we can use this to determine the number of pixels it takes to create one mil, whatever distance you want to determine. Now, if 1,000 microns measured here is equal to a line, which we've drawn here with an ROI, which is equal to 472 pixels. Therefore, if we divide the number of pixels by the number of microns, that means that every micrometer is 0.472 pixels. Or if we take it the other way around and divide the 1,000 microns by 472 pixels, each pixel is 2.11 microns. So there's our calibrations there. And it depends which sort of software. Both of these are identical. It's just presented a different way, and you will need to see, depending on which software you use, it may calibrate things a different way. So what we're going to do is we're going to calibrate an image. So let's go back into FIJI, and we're going to grab, in part 1, we're going to grab the stage micrometer image. So I'm going to bring that up, drag that and drop that in. And we can see immediately that there is no scale information. It just says that this image is 1360 by 1024 pixels. So what we're going to do is we're going to draw a line. We're going to select our line tool, and we're going to draw a line across a certain distance. And it doesn't matter which distance you draw this along, as long as you know what it is. Now I'm going to draw it across 1 millimeter or 1,000 microns, or if I really wanted to, I could draw it across 2,000 microns. As long as I know what that is and I input the correct value, it doesn't matter. I could do 500 or 550, it doesn't matter. But I'm just going to do across 1,000. Now, if I want this line to be completely straight, I can hold down Shift and draw straight down to the position that I want to be in. So if I zoom in a bit, you'll see that I've drawn to that line. And if you want to modify it, you just select one of any ROI, the line tool if you want, and then just grab it and then drag it to where it needs to be a bit more accurate. And then I'm just going to zoom back up and make sure that this is on the correct part of the line. Now this image is on a slight jaunty angle, so I am just going to have it not completely straight, but on the similar sort of angle. So what I'm going to do now is I'm going to go to the set scale function, and you'll find that under Analyze and Set Scale. So this will give me the information I need in order to correctly give this image a scale. Now, automatically, the distance in pixels has been derived from the line that I've drawn. Whatever line you draw, that distance will be automatically inputted in here. Now, you can change that if you want to, if that's for whatever reason is inaccurate, but it will take that information. The known distance, I know that this is 1,000 microns. So I'm going to type 1,000 microns into that. The pixel aspect ratio, as I said before, for all intents and purposes, we assume that every single pixel is identical in X and Y. It's probably not at some scale, either in the nanometers or picometers or whatever scale you're using. But for our purposes, we just assume it's 1-to-1, all one. The unit of length is obviously microns. So you can either say micrometers or microns. It doesn't matter. You can use like a U, or it doesn't matter. So I'm just going to write microns just because. And I'm going to click OK. Now, there is another little button here called Global. If I click the Global button, every single image I open up after this one has been calibrated will automatically be calibrated. So it's a good little function if you've got a whole bunch of images that haven't been calibrated that you then want to calibrate very easily. If I want to click to remove the scale that's already on there for whatever reason, if I want to just put it back to a pixel image, I would click that and it will remove it. Now we can actually see down the bottom that the scale is 475 micrometers per pixel. Now, if I look back here, it's almost exactly what I measured when I wrote this slide. It's slightly out, but it's close enough. Bring up the image again. Okay, so where's image JCOR? Oh, it's disappeared. So now if I click OK with this particular scale here, and I bring that image up, which has now disappeared, we can see that this image is now calibrated by microns. So what I'm going to do now is I'm just going to measure, just as a test, I'm going to measure this distance here, which should be 100 microns. And what you'll see is in the display up here, you should see the measurement as I draw. Oh, maybe if I don't cover it, that would help. So if I draw along here, you'll actually see the length, which is there, go to 100 micrometers there. So close enough. So 101, I'm pretty much bang on almost. So that means that I've now calibrated that. Now, you might be asking yourself, well, where do I get a stage micrometer from? Now, stage micrometers aren't cheap, and if your lab doesn't have one, it's very unlikely that they're going to buy one. They're several hundred to $1,000. However, what you can use is a hemacytometer, because the hemacytometers have known distances etched via lasers or whatever, however they've done it, with specific values, and you can actually get the value off the hemacytometer. So that's a nice, and most labs have hemacytometers, so you can use them in place of a stage micrometer. Now that we've calibrated our image, we can create a scale bar. A scale bar without a scale, calibrated scale, will not work. So let's bring up our image again. So what we would do is I'm going to zoom out, and I'm going to click off my scale that I've just added. Now we're going to go to Analyze, Tools, and Scale Bar. Analyze, Tools, Scale Bar. And that will bring up the scale bar. Now, automatically, you can see the scale bar has already been put into place, because by default, it's put into the lower right. Now, you can change that position. By convention, we always use the lower right. Who knows why that is? It just seems to be. But if you want to be a trendsetter, you can put it wherever you want. Put it at the center if you want. If you actually have a. So if I put, now see if this works. Now if I put a little box here in the middle, and I try to add a scale bar at selection, it'll actually put it wherever my ROI is. But I don't want to do that. I'm going to put it in the lower right where we all have it. The width in microns. Now the width is the width across it. Now it's just essentially use that line that I've created here as a template. Now I actually might want a more round number than whatever this one is. So I'm going to say I want my scale bar to be 500 microns in width. I want the line thickness to be 10. So I can make it bigger. I want my font size to be bigger than that, 40, so I can actually see it. You can change the color. White works really well for a transmitted image, but sometimes it can be a bit washed out by everything. So you may want to add a different color. Black's probably not going to work very well for this. So I'm going to put white, but I'm also going to put a background on it just so it stands out. So I can put a black background around it so it actually stands out from the rest of the image. Now, down the bottom, you've got a few tools. I'm just going to go and ignore that. They're mostly text tools. I mean, you can change it to vertical if you want to, rather than horizontal for whatever reason. The main one I'm going to talk about you also hide the text. The main one I'm going to talk about is the overlay function. Now, at the moment, the scale bar is existing as an overlay on top of my image. Now, if I save this as a TIFF, most Windows picture viewers can't see layers or overlays. So you won't actually see anything if you try to overlay this. Now, if I turn off the overlay, what will happen is we will what's known as burn in the annotation. So this annotation will be burnt into the image, and it will be part of the pixel information. So do that at your own peril, and if you are going to do that, make sure you save this as a separate image file. Because otherwise, if you save it over top of the original data, you'll lose whatever was sitting down there. So if I click overlay off and OK, then it's going to now be part of, if I zoom in, it's going to actually be part, you can actually see the pixels made up. Whereas if I did it as an overlay, so if I go back to Tools, Scale Bar, lower right, you'll see it's actually, it actually does it as a proper overlay. But however, if I click overlay off, you'd actually see the actual pixel information. So now that's burnt in. So I'd save that as a TIFF or whatever I want, and that information will now be part of the image. The ROI manager, which I've mentioned previously. The ROI manager allows us to add ROIs, multiple ROIs to our image. So if I bring back image FIJI and add an image. Now, if I wanted to zoom in and I wanted to select an image, like I select a cell. Now, if I draw another one, it will the other one will disappear. So what I can do is select that, and if you click Control T, the ROI manager will appear, and now so this will give you a list of ROIs. So now if I go to the ROI tool and I draw another one and click Control T, the other one has disappeared, but it is still in the manager. So if I go click Show All, you'll see all of the ROIs that I'm adding. And I'm just clicking Control T, or I can click Add if I wanted to, and it will just slowly make this up. And each one of these I can select individually for manipulation. So if I click all of them and I click Delete, oh, no, I can't, sorry. Delete, so I can actually delete all of these. So you would click Delete, get rid of them, and then you can add them all again if you want to. And they will just, and you can do that with any number of ROIs. It doesn't have to be just one type. You can do multiple ones. So you can then use these for different analysis. And you can actually analyze these all at the same time, but we'll get to that in another part. So annotations can be used to draw the attention of specific parts of the cell. So if I bring up my ROI manager, and I'm just going to delete everything, select everything, delete. Now, if I'm interested in this cell here, I can, oh, wrong tool. Here's my, okay, select my box. Oh, it's too many windows open. There we go. I'm going to do this one. So if I select this image and I say I want to highlight this, and I'm going to select T, and I'm going to add that to my ROI manager. Now, the ROI manager, if it disappears, you should be able to find it in your window tool. It'll just be there. Then I can add an arrow. So you have arrows. If you go over here, you should be able to find an arrow tool here. So if I click that and add an arrow, I can add the arrow, add that as an ROI, and then I can do text. So if you highlight the text thing and then draw a box, it will then allow you to type, "This is very interesting," or whatever you want to. You can then just spell very right. Interesting. You can change the color by double clicking on the color tool here. So if you double click on that, it will bring up the color window, which is there. And then you can change it to whatever color you really want. Now, the problem with the text tool is you can't use Control T to add it to the ROI, because it will literally just draw a T. It'll type a T. So you have to actually manually add it to the ROI. So now you've got these. So now if I select all of them, now I've got my annotations. You can add as many annotations as you want. Now we were talking about burning in before with the scale bar. You can burn in all of these ROIs. It's a good idea to deselect them by clicking in the image somewhere, so it removes those editing points. So if you click in like that, it just leaves them as is. Then if you click the flatten button, it will actually flatten the image and create those as burnt in pixels. It'll duplicate the image, so you've got a duplication, but it will have just those annotations burnt in as pixel information, which we'll talk about there. So yeah, that's the basic functionality of FIJI. So we're going to go on to part 3, which is image manipulation. So the word manipulation and image analysis has a bad rap because it makes it sound like we're doing something dodgy. However, any image that you've seen has probably most likely undergone some degree of manipulation with contrast or brightness. Now, if used correctly, image adjustments can help emphasize features within your image. The proviso being, if any manipulation that you've carried out, it must be linear, which means applied to the image as a whole. You can't just select individual cells and make them brighter. That doesn't work. You make them all brighter, but not individual cells. The same adjustment must be applied to any other images that are being compared. So if you increase the brightness by 10% in one image, you should be increasing the brightness to every single other image. And if you're unsure, if you've gone too far, just ask yourself, has the adjustment skewed the outcome? If you've turned a negative result into a positive result, you've skewed the outcome, and vice versa. So just keep that in mind when you're doing this sort of thing. The image histogram. If you've used a digital camera, you've probably seen the image histogram in the display, the LCD display of your camera. It's a type of graph which is a representation of the tonal distribution of the digital image. That's literally just saying where the bright stuff is. So it plots the total number of pixels for each tonal value from gray, and the tonal values which are graded values. So down this end of the graph, we've got the low level, so the black pixels. 0 is black. So these are your shadows. In the middle, you've got your midtones, and then you've got your highlights. So these are the brighter pixels. 255 being white. So you've got this entire range of pixels. Then you've got the number of pixels with that particular value, which gives you this sort of brightness graph. So it gives you an ability to judge the entire tonal distribution. So if you sort of see the tonal distribution being skewed this end, then it's too bright. If you see the sort of graph skewed this way, then you've probably got a lot of very, very dark pixels, which is usually what you would see in a fluorescent image, but not so much in a transmitted bright field image. Now, every digital image has a histogram because that's just how it works. So if I open up another image, which is the DAB black and white from our resources. And then if I go into analyze histogram, analyze histogram, you'll actually see the histogram for this image. Now, this image is skewed a little bit too much to the right side, which means it's a little bit brighter than it probably should be, which is fine, but depends on the type of image that you're looking at. We would, in a perfect world, you'd probably want that brightness graph to be right in the middle, which means you've got not many dark pixels, not too many bright pixels, but a lot of sort of mid-range where the data should really lie. Color images also have a histogram, but they typically have 3 separate histograms. So in a black and white image, you've just got the different gray colors. Because the RGB images are made up of red, green, and blue, you typically have a histogram for each one of those, and the combination of them actually creates all of your primary, your secondary, and your tertiary colors. So that's how you get that sort of distribution in a color image. And you can, if you go into the color histogram image. So if I instead open up the DAB color image and look at the histogram, so analyze histogram, you'll actually see the RGB button. So this is just the general grayscale image, which is very similar to the grayscale image version of this. Now, if I can cycle between the red, the green, and the blue, you see that they have different values depending on the colors that are actually in here. So that leads me to bit depth. So I know it seems like a bit of a jump, but it actually it will be very obvious why we're going straight to bit depth. So bit depth is a representative of the number of tonal values which are in the image. So the bit depth tells us the total number of shades or tones of a color that are available in a certain color palette. So we've all heard of 8-bit images, 16-bit images. That's what that's the bit depth. So the bit depth number can be calculated as a 2 to the power of, where n is the number of bits. So an 8-bit image has 2 to the power of 8, which is 256, which has 256 shades. A 16-bit image is 2 to the power of 16, which has 65,000. Now, typically, the more shade, the higher the bit depth, the more information you can typically glean from the image. So what does that have to do with image analysis? And you see a sort of a graphical representation of 1-bit versus 2-bit up to 16 bits. And you sort of see as you go up, the delineation between the different bit depth disappears as the difference between the shades essentially evaporates. So if we were going to measure this leaf with a ruler, and we had on one side of the ruler centimeters, and on the other side we had millimeters, which scale would give you the most accurate measurement? Now, if you're looking at the centimeters, we can kind of eyeball that and say, well, this leaf is about 4.6 or 4.7 centimeters. However, if we go to the other side, we've got more graduation between these values, and we can actually say, well, this leaf is exactly for 46 millimeters or 4.6 centimeters. And of course, if we went down to the micrometers, we can get even more accurate information. So the more segmentation the scales have, the more information we can actually get from them. Now, the opposite here is that if you look at the two different bit depths, 4-bit and 32-bit depth of the same object, if you converted this into the raw image into either a 32-bit or a 4-bit, the 32-bit image might look a lot smoother. However, if we look at the 4-bit image, because a lot of the pixel values have been what's called binned, and we'll get into binning a bit later, you'd actually see the veins on the leaf a lot clearer in the 4-bit image. The 32-bit image, because there's a higher number of shades of the color, they tend to blend into one of them because the difference between them is much, much less. However, with the 4-bit image, because everything's binned down, we can actually see the veins a lot clearer. So it depends what you're doing. So the higher the bit depth, the more information we can gather. So especially in regard to the intensity values. Intensity values are always better when we have a higher bit depth, because we can sort of, if you're comparing two separate images, you can often get a bigger difference between two images with large bit depths. It improves the overall resolution of the details by separating the colors into finer increments. However, sometimes we need to lower the bit depth to blend color shades to create masks to aid analysis, or as we saw with the leaf, to actually bring out more detail, but it will very much depend on your application. So if we look at this image here, this image is a 1-bit gray image which is 2 to the power of 1, which is 2 shades, which is also known as a binary image. So the pixels are either black or white. So by using this image, bin down to a binary image, we can see very clearly the object versus the background. The object is very black, whereas the background is very white. So it's very easy to create the mask. Now, I can obviously see that that image is a hamburger. However, trying to get that detail with other objects may be difficult. So if you add higher bit depth, so if we increase the bit depth a little bit, it brings a bit more information. We've now got a 2-bit gray, 4 shades, which is either black, dark gray, light gray, or white. And we can start to see, rather than it being a blob, you actually start seeing the layers of the ingredients within the hamburger, as well as the table that it seems to be sitting on, park bench, I'd assume. And as we add more and more shades of gray, we get more and more detail until we can actually see the best possible detail which we can have with this 8-bit gray image, which is 256 shades. Now, just remember that every single digital image is usually made up of multiple grayscale images. And what I've done here is I've colorized each of the different red, green, and blue channels in their separate colors. And when you merge them all together, you actually get the full color image. So a color image is literally just made up of a grayscale blue channel, a grayscale green channel, and a grayscale red channel. These have just been falsely colored. These could be whatever color I want, but to make the actual final image, they need to be blue, green, and red, which combined create the final image. So this is a 24-bit RGB color, which is made up of 16,777,216 possible color combinations within the RGB color space. So why is bit depth important? So increasing the bit depth when acquiring images gives us a much more pixel intensity information, which is especially important for image analysis. Now, the image also tends to look a lot smoother because the colors tend to blend in a lot better together. Now, Microsoft Windows often has issues with viewing any data which is, I think it's 12-bit. It's either 12-bit or 14-bit. Anything over 12 or 14-bit, it just can't actually show you because it just doesn't work in that color space. So often we have to use either image J. Say we have a 16-bit image, we would often have to use either image J or Photoshop or something like that, because if we opened up with Windows default image viewer, what you often see is just a black screen because it can't actually show you the full 16 bits. It can only usually show you the first 12 to 2 to the power of 12 shades. But if you want to get that extra information, you have to use an actual specific imaging software. Now, lowering the bit depth does lower the file size by reducing the amount of information, making it suitable for email and small storage drives. Now, we're at the terabytes of file storage at the moment. I mean, you can get petabyte servers at the moment. So image storage isn't usually a problem at the moment. But back in the day, trying to send a TIFF through email was just terrible. So we usually have to put it down to a JPEG, which is very compressed. So that's why we would increase or decrease the bit depth. Now, just these are the sort of artifacts that you might actually see if you reduce the bit depth. So you get these what's called posterization artifacts, which is where the shades of the colors are actually binned down. Rather than being a very fine increment, they actually bin down into rougher increments. So that makes up for the reduced color resolution. So that's a possible artifact that we get. Now, changing bit depth is very simple. You would go and you would open an image and you would go into image type, and you would you would change the bit depth using that functionality. Now, bit depth should not be changed in the original images. So if you want to create a separate if you want to create a lower bit depth image for whatever reason that you're using, you should always do it in a duplicate and do not save over your original data. Just remember that increasing the bit depth, say if you have an 8-bit and you want to convert it to a 32-bit, it's not going to add extra information. You can't create something from nothing. However, you can decrease the bit depth from a higher one. Decreasing the bit depth destroys information, so it bins it down into a lower amount of energy, a lower amount of information. So just remember that. And if you have to change the bit depth, make sure you duplicate the original image. That leads me into brightness and contrast. So brightness and contrast. So often we need to adjust the image in order to improve the appearance when we're presenting our results. Now, most images that you see in publications will probably have some degree of contrast or brightness adjustment. Now, proper microscope setup should be observed at the time of acquisition to minimize these adjustments. If you set up the image if you set up the microscope in a terrible way, you're going to get a terrible image. So you should always make sure that your imaging device is set up perfectly as much as you possibly can, because FIJI is not a miracle worker. It's not a miracle cure for bad microscopy practices. So garbage in is equal to garbage out. You can fix some things, but not everything. So when in doubt, ask for help from whoever is in charge of that imaging system. And I'm always available for assistance. So we've got a function in ImageJ for changing the brightness and contrast. So I'm just going to grab ImageJ there again. And I'm going to open up the DAB black and white image. Now, brightness and contrast. So brightness increases the overall lightness and darkness of an image, whereas contrast will adjust the difference between the darkest and the lightest pixels. So by accentuating that difference between the darkest and lightest pixels, you actually bring out a lot more information. So I'm going to bring up my brightness and contrast. So that will be under Image, Adjust, Brightness and Contrast. And it always goes off onto I have 4 screens, so it always goes off into one other screen. So this is my brightness and contrast function. So by reducing the minimum, what we're doing is essentially altering the darkest pixels, altering the lighter pixels to be darker pixels. So any pixels which are down below this line are made darkened as we sort of move forward. So if we move this right to the end, everything becomes darker. And if we do the opposite, everything above this line becomes brighter. So everything eventually will become to white. So by using a combination of this, you can actually change the image to give you a bit more information. So if I reset everything, that's the basic information there. Now, if I click auto, it does an okay job, but I never trust auto because it can sort of give you weird results. So what I'm going to do is I'm going to use my minimum slider, and I'm just going to drag it up a little bit. And what that will do is it will make the darker objects darker, but make the contrast higher. So essentially it brings out that detail, which looks a little bit washed out in the original image. So if I bring this down, that makes that data darker. Now, if I bring up the other end, it actually improves the brightness. So you actually go from a fairly washed out image to a higher, and you can see the contrast automatically adjusts based on what I'm doing. And I can adjust that and it will move by sliders, but I can get a more finer view here. So if I adjust this by eye, there are no rules with this. You adjust it by eye until you sort of see the image as you would like it to be seen. So if I want to bring this is dab staining here. So if I want to make the dab staining look a little bit more contrasty, I can play with this until I get it to a state where I'm happy. And that's much better. So I can actually see the contrast of the dab against the rest of the tissue a lot better. Now, if I click reset, you'll see that it goes back to that horrible washed out image. Just remember, you're not adding or destroying data. All you're doing is just changing the way the image is displayed. However, if you click apply, what it will do is it will take that new pixel values, all the brightness. So if I go back to that image, which is there, and I bring up my brightness and contrast, which is there. And I'll need to see image J as well to prove this. Now, if I go into the background and I hover over the background, you'll see that the value about there, the value of those pixels is about 221. Now, if I make them horrendously bright and I hover there, they're still 220. I haven't actually changed any of the data. It's just I've changed the way that it's displayed. Now, if I then make it really, really bright and I click apply, it's going to ask me, the pixel values will change. If I click OK, these pixel values are now 255, which is the brightest that they can be with an 8-bit image. So I've actually destroyed the original data. Resetting doesn't bring everything back because I've now altered those pixel values irretrievably. I'd have to go back to the original data. The color balance, if you want to, you can try and edit the color balance. I find that editing the color balance can be a bit difficult because trying to get a balance between them is very difficult without making everything look really terrible. So if I go to adjust color balance, and you can go through. So if I alter the red, I can make the red brighter. I can make the green brighter, but trying to adjust them in a way that it doesn't look really weird. You have to get those red, green, and blue perfect in order for it to, I suppose that's all right. Yeah, I suppose that's all right, but it's very hard to find that balance. Now, typically on any imaging system with a camera, you'll find a button which is called white balance, and you should always do your white balance at the microscope. Trying to do it via software is just a pain. So it is there if you want to try, but yeah, just trying to get that color balance correct can be very difficult. And it's just a bit more white balance. I've actually got a script which I wrote which does it pretty well, but I always find it just easier to do it at the camera. Lookup tables. Now, as I said before, every single digital image you've ever seen in any fluorescent images or anything like that are typically made up of false colors. So I'm going to, so essentially what you have is a pseudo color or false color, which is colored using a color generated lookup table palette. And it's very easy to use those in image J. So what we'll do is I'm going to open up in our folder, I'm going to open up the 3-channel fluorescence, and I'm just going to drag and drop cytoskeleton green in there. And by simply going to image and lookup tables, I can choose whatever color I want. Now, to make life easier, there's actually a button up the top called Lookup Table. So if you click on LUT, it gives you that. Now I can color this green, which is what the original color was. Or I can make this rainbow or grayscale again, fire, which is kind of a predator vision or something. So you can make that whatever. Now, I'm not changing anything regarding the pixel values. Whatever pixel values are there, it doesn't change. You're just literally changing the way that we're perceiving that color there. So you've got basically a heat map. These are the very sort of those very, very bright parts. It actually highlights where the bright parts of this image are, and everything else is a bit duller. So you can use the lookup tables to change the way that we perceive that data and to highlight certain objects. And as we will see in a second, to discern between different channels. So merging channels, often if we've captured images separately, I'm just going to delete some windows that I've got open. So too much stuff open now. So I'm going to open up all 3 of my three-channel fluorescent images. I'm running out of time. All 3 of my images, and I'm going to drag and drop them into image J so I have all 3 there. So merging channels is fairly simple. The only thing is the images have to be the same bit depth. You can't merge a 8-bit, 16-bit, and 32-bit image. It doesn't work. As well as the XY pixel size. So the images should be identical in their X and Y pixel values. You can't merge odd shaped images. So if one's 1000 by 1000 or one's 15 and one's 2000, you can't do it. So Merging images is very simple. So all you would do is you would bring up image J, you would go into image, color, merge channels, very simply. And it will look at all of the images that are open. I've put them off screen, but they're still open. So you've got your red channel, green channel, blue channel, a gray channel, cyan, magenta, and yellow. So you have the possibility of merging 8 separate images. So I'm going to grab as red. I'm going to call that mitochondrial red. Green, cytoskeleton green, and blue is going to be nucleus blue. I'm going to create a composite, which I've never understood the purpose of this button, because if you click it, if you unclick it and click OK, literally nothing happens, because that's why we're here. We're creating a composite. I'm going to keep the source images open, because if you don't click that, all of the images disappear and they're merged into that one. But at least if you make a mistake, you can then go back. Ignore the source lookup tables. That can affect the way the image comes out if you've already applied a lookup table. So I usually click ignore the source lookup tables, and then I click OK. And then we get this image here. Oh, I have a message. Minus 2472. Oh, perfect. Well done, Timon. That was sorry, that was a while ago, but yeah, fantastic for getting exactly on the nose. So now we have created this multi-channel image from the 3 images that we have open, and it's called composite. We can rename that whatever we want, and it is a red, green, blue. So if I zoom in, we can actually see the 3 image channels which have now been colorized by that create channel. Now you'll actually see a slider down the bottom, and we can actually individually select each one. You see the color changes and the name changes as I go. Now this doesn't have any particular applications at the moment, but if I go into image color channels tool, I can change it from a composite, which is what it is showing me at the moment, where everything is on top of each other, to color. And it actually allows me to cycle through each color individually. The other one is grayscale. So if I want to go back to grayscale, I can turn off the color. Under composite, I can turn channels on and off if I want to, just by using these. And there's some extra functionality, which I'm not going to go. You can change the colors of the lookup tables here. I'm not going to go into that. But that allows us to create that color image. Now, just as we have a merge image, merge color channels, we have a split color channel. So if you've got a multi-channel image and you want to split apart the channels for analysis or manipulation or whatever, you would go into image, color, split channels. And that will now split the color channels, but it will maintain that lookup table that was added by the channel merge. There's the channel tool that we were just talking about, and splitting the channel. So now you have the colorized channels that you can then do whatever you want with. So that's part 3 all done. We'll go on to part 4, which is multi-dimensional images. Now, technically, we already have been dealing with multi-dimensional images. The images that we've been looking at the moment previously, they have an X dimension, a Y dimension, and a color dimension. So we have already been dealing with this, but this is moving into the more of the 3D time, 3D time space. So stacks are used to display and analyze images that are related to each other. So we've already looked at one stack, which is that color stack. We could actually cycle through the 3 channels. Now, allowing us to, if we capture images over time, we can stack them in such a way that that little slider bar allows us to manipulate time within the image. Now, if you were looking at, for example, mitosis in a mammalian cell, mitosis takes about 24 hours. Now, if we were to watch that ourselves, not only is that incredibly tedious, but our eyes don't really let us visualize quite well the minute changes that would occur in mitosis over time. However, if we capture that process over 24 hours and then speed the process up, we can actually see mitosis occurring in a much shorter time span, seeing those differences as we go. Now, stacks of spatial data can be animated and measured. If we will be looking at analyzing temporal images like over time in part 2 in a few months, but it is completely possible. So FIJI uses what's called a hyperstack, which is multiple different slider bars, which allows us to manipulate in channels, Z, so through a Z stack and over time. You can also add multiple stage positions if you've got multiple stage positions, but generally we would use a channel, Z, and time. Opening the data sets. So you can typically use the bioformats importer in the plugins, but dragging and dropping works pretty well for this. So what I'm going to do is I'm going to bring up FIJI again, and I'm going to grab in this data folder, I should have the zeiss.lsm multi-stack image, and I'm just going to drag and drop that in, and it should just open straight away. Now this image has channels, it has Z and time. So if I go through the Z tool, you can actually see a Z stack of the cytoskeleton, or might be mitochondria, I'm not sure. You can also go over time. Time doesn't actually do it. Time doesn't do much. There's very little changes, but if there was sort of animation, you can actually see that. And then the channels, you can actually go through the different channels of that image. Now, if you opened it up via the bioformats function, you would get this extra information. Sometimes it happens automatically. Sometimes we have to sort of push it. So what I'm going to do is I'm going to go into plugins, and I'm going to go to bioformats. And you remember the bioformats I was talking about before. Bioformats is the group of people who their job is to make all of the different formats function well within ImageJ. So if I go to bioformats importer, and I go into Zeiss, it will open up this bioformats window. So the bioformats window allows me to change specific functions. Now I can, if I wanted to, a very basic sort of function is I can actually split the channels, focal planes and time points into separate images if I really, really wanted to. I can change the view. I don't recommend doing that. Hyperstack is usually the best way to go. You can change the way the color is changed. So if I want to view it as a composite by default, I would change it to composite, or I can see it as colorized, so separate channels automatically. So if I go composite. The other thing there is the virtual stack. Now, virtual stack is really handy if you have gigantic images. So if you have gigabytes or even terabytes of image files, then what you can do is use the virtual stack. What the virtual stack does is, rather than open every single dimension, every single channel, every single image in the hyperstack, it only opens the one that you're interested in at the moment. So as you are going through the time slider, it's only opening up each time point and closing the other one. So it's really handy for looking at really, really large data sets. Now, if I click virtual stack, it's really not going to do anything for this one because it's actually really small, so it doesn't matter what I do. So if I click OK, that will then open this up. And then if we go through the Z, you actually see it's instead of the individual channel, because I set it to composite, it's showing me the composite. Virtual stacks there. Color options, as we said, we can change the different color options. You can change it to a custom color. You can actually change the color that each of those channels opens as. Rather than blue, green, red, you can have it as red, blue, green. But most of the time you will either want composite or colorized. Images to stacks and vice versa. So sometimes we need to convert a sequence of images to a stack, or we want to change a stack into a sequence of images. So if I bring up ImageJ again, and I've got my stack here, what I can do is go into image, what is it? It's image stacks, and I'm going to turn my stack into a series of images. Are you sure you want to convert this stack to 300 separate windows? No, I'm not. The reason there's 300 separate windows is you've got 300 channels, a certain number of Z stacks, and a whole lot of time points. So it's actually going to open every single one of those into separate windows. I'm not going to do that because it's just going to be too cluttered. However, I do have the opposite. So under test stack. So test stack, is literally just a series of numbered windows, 1, 2, 3 to 6. So if you want to open up a sequence of images as a stack, all you would do is drag the folder into image J. It'll ask you a series of questions. I typically, you can open them as separate images rather than a stack. I typically leave everything as default and I click OK. And now I have these separate images converted into a series. Now it's usually pretty good as long as you've got everything named in sequence. If you've got sort of a random numbering system, it does have a lot of trouble with it. So make sure that if you are going to do that, make sure they're imaged, they're labeled something 1, something 2, something 3, just so it knows what to sort of pick. So from there, we can now change this into a bunch of separate images. So if I go now into image stacks, stacked images, it's going to separate that out into 6 separate images. Now I'm going to do the opposite, and I'm going to go to stacks and images to stack. Now I've got a number of different images. I've still got all those 3-channel images from before. So what you can actually do is use the filter here, and I'm just going to say the image, the title contains image, because this is image 1, image 2, image 3. So I'm just going to say the title that I want to be part of this contains the word image. And if I go OK, it has now converted that back using the number into the stack that I wanted. The stack sorter is a really good tool to have if you are doing that, because if things go wrong, you can use the stack sorter to fix it. So let's just pretend that my image sequence was incorrect and one of these slices, say image 6, got put into the wrong position. So what I can do is go into image, stacks, tools, and the stack sorter. It's gone to a different window. So there we are. Now you can use this to move stacks around. So if I want to put position 6 to the first position, I will press first. And now image 6 is now down the opposite end. And again, I can go last, or I can move it through the different positions within the stack to whichever position I want. I can duplicate that to a separate, so I've got 2 6s now, and then I can delete that particular stack again. You can delete a certain number and reverse. There's also a reverse here. So if I click reverse, I've now reversed the order. So there's a whole lot of different functions in there, which makes life a lot easier. 3-dimensional data. So that's the channel, looking at sorting channels and sorting the positions. But now we're looking at going from XY to the 3rd dimension, so 3D images. So this is dealing with voxels. Now, ImageJ has some functionality for visualization of 3D datasets. However, we have much better programs specifically for it, like Amaris and Drishti, which are free to use, which are more suited for analysis of 3D volumes. But you can, if you're in a pinch, FIJI will help you out. Maximum intensity predictions. A lot of the Zs, if you've got a publication, it's very hard to put a Z stack, a 3D Z stack into a 3D into a publication. I mean, obviously most publications are PDFs now, and you can have videos and things like that. But back in the day when it was mostly print, we had to do something in order to make that data into essentially a flattened image. So what a maximum intensity projection does is it takes all of the imaging data and it takes the brightest pixels and moves them to the front above all of the darker pixels. Essentially flattens everything down into a single image. So what I'm going to do is I'm going to open up my FlyBrain. So I'm going to go into File, Open Samples, and FlyBrain, and let that download. Actually, there we go. So there's your FlyBrain. So this is a Z stack. Now we could create something to go into a publication using the sort of maybe a video or something. But if we just want a flat image, what we can do is to select the image. Oh, shake. Every time I shake it, everything goes away. Get rid of some data because it's getting a bit cluttered. And remember, double click, clears your memory. And what I'll do is I'll go into Image, Stacks, and Z Project. So Z Project will flatten it down to a single frame, but it'll show you a lot more data based on the intensity of the data. Now, there are a few different functions. So if I go over here, you'll see what happens when I try to do the different projection types. So either using a maximum intensity, average intensity, or standard deviation. Now, maximum intensity can go really, really wrong if your data is quite bright. You see everything is quite washed out. Average intensity, again, depending on your data, can go a bit sorry, just close the door, can go a bit wrong. And in this case, it gives us a dark image. However, I tried the standard deviation and it gave a really good value. So my advice is to try different functionalities, different settings within ImageJ to figure out what's best to show the data that you want to do. So I'm going to show the data that you want to show. So I'm going to go into Image, Stacks, and Z Project, and I'm going to choose the standard deviation. I've tried all 6 of these, and standard deviation is the best of them all for this data set. Not necessarily your data set, but this data set. And I click OK, and it gives me a flattened image. So all of the sections in here have now been flattened down to a single image. The pixel value that comes up to be seen was based on the standard deviation of all of the pixels. So that just gives us a more realistic view of what's going on. So I'm going to keep this image for the next part. So if I go to the next part, we look at orthogonal projection. Now what this has done is it gives me a pseudo three-dimensional view of the top and the side, both sides of this data. Now it's giving me cross sections. So essentially it's like I've cut using this this cross here. I can use it to cut through a section to see what it would look like if I actually cut the brain in that particular part. So I'm going to go back to ImageJ, and I'm going to go to Image, Stacks, Orthogonal Views. So now using the cross here, I can use that to select the cross section across here to see the view here and across here to see the view if I'd actually cut the data. Now this works both ways. I can actually go here and see the view if I cut along this part to what it would actually be seen here, and this part is what I would see with the other views. And you can then save these images as TIFF images to show what the cross section would look like. So if you're interested in the hippocampus or these lobes, you can actually get a cross section about what actually is going on in there. Slice montage. Slice montage is really good if you want to show specific increments of the data stack. This could be over time, over Z, and can be used to create a montage that you can then produce as an image. So I'm going to pick up my FIJI again, and I'm going to grab my FlyBrain, the original data. Now, in this case, this is a Z stack, so I'm going to show this as a montage of the data. I'm actually going to close that. I think orthogonal projection is still open. There we go. So I'll close the orthogonal projection. And you can do that by just closing one of the images that was open. So the montage, I'm going to bring up the montage window, which you'll find in Image, Stacks, and Make Montage. So this gives you a bunch of options. Now, it's a good idea to know how many images you have, because that'll allow you to select the number of columns and rows that there actually are. Make Montage. So I know that this image has 57 Z stacks. Now that's close enough to 60. So I'm going to just pretend that I have 60 Z stacks. Now I could present this in a number of different ways. I could do 10 columns with 6 rows. I could do 60 columns in 1 row. It depends what you want to do. So I'm just going to say I want to do 60 columns and I want to do, 6 columns and I want to do 10 rows. So that will create my 10 images as part and show each one of these Z stacks in a separate image. The scale factor is how much I want to downgrade the resolution. Now this is done, the default is to downgrade it to 1/4, but I'm going to actually use the full resolution by clicking 1. I want to use the entire range from 1 to 57. If I know that maybe 1 to 5 doesn't have anything, then I can just skip straight to 6, but I'm going to include the entire range. The increment is how many slices ahead I want to go. Now, if you want to use every single slice, you would do 1. You want to increment each slice by 1. If you want to maybe show every second image instead of every one, you would do the increment as 2, and so on and so forth. The border width, you can create borders between each of the images that are going to be put into the montage. I don't tend to use borders, but you can create, and this is the number of pixels. So if you wanted to put a 5 pixel border between each of the image, then you would just write 5. And font size, if you want to add a label. I don't usually add a label because it makes it look a bit cluttered. All it does is it shows you the Z stack that each one of these images in the montage are for. You can do that later if you want to, but you can add a slice label. And if you want to use the foreground color as the color for the label, you can do that. I tend to not, but I'm going to turn off the label slices because I don't like to use it. I do labels in Photoshop and things like that. And then I click OK. And then invalid number. Okay. What was my invalid number? What's my invalid number? Okay. Oh. What did I do? Okay. 6 times 10 is 60. Scale factor 1. First slice. Border width 0. Increment. I don't know. Where's the problem? What size? Border width 0. Oh, I don't know what the problem was. Maybe I put an apostrophe or something and it's got rid of it. But yeah, there we see all of the slices that we had in one entire montage. So it allows you to a publishable image that you can use to show off that 3D data. Now that's a pretty big montage. So what I can do is instead I can say, well, I want to instead use every second image instead, and I'm going to have let's have a look, for 30. I'm going to have 10 columns and 3 rows. So I've got 30 images now. If I go OK, then we get a smaller image, and we've skipped every second image, and it's a bit more realistic as an image. Simple 3D volume viewer. So we can actually produce a 3-dimensional image using ImageJ, which you can then which you can then turn into a movie if you wanted to. So I've got my raw data there again, and I'm going to go into Image, Stacks, and 3D Project, which brings up this view. Now, again, there are 3 different options, which will give you 3 different results. I found the mean value for this to give the best results. I'm not going to go through all 3 of them, but it will depend on your data. I'm going to rotate around the y-axis, which is around there. You can rotate around the x-axis, so it rotates that way. You can also rotate around the z-axis, which will rotate which way that way. So a kind of weird way, but y-axis is probably the easiest because it'll rotate around the y-axis around like that. The slice spacing is taken from the data, the voxel data. If you make this bigger or smaller, the image will expand, the 3D image will expand or be shrunk down. So I'm just going to leave it to the slice spacing because that'll make it look realistic. If you do your projection and it doesn't look right, then you can modify that to basically plump up the image to make it look correct. I'm going to do a full 360 360 rotation. So the initial angle is 0 position, round full 360. So 360 and 0 are obviously the same, but 0 is the start point and 360 will be the end point. I'm going to increment this in 10-degree increments. So every image created will be a 10-degree rotation. Transparency, I don't typically mess with. If you want to make the image look a little bit more transparent, you can mess with these transparency and opacity settings. I can never remember what the surface depth cueing does. I just leave that as the default. I keep meaning to look that up, what that actually means, but just it's never caused me any problems before. The very important function that you should collect on is interpolate. Now, what interpolate means is it makes a more smoother transition between the different sections. So this is without interpolation. So you can actually see there is no sort of smooth transition between each of the sections. And this is with interpolation on. Now it takes a little bit longer, but I definitely recommend it. So I'm just going to leave it as like that and click OK. And there we go. So now this looks very, very much like that Z stack that maximum projection Z stack that we did. However, now we have a little slider bar. Now, if I click this, we can then rotate it around that y-axis, and we can actually get a 3D image. Now, you can then save this either as a TIFF series or as a movie. So if you go into here and go File, Save as AVI. I tend to not use compression for small images. If you use compression, you can actually reduce the resolution. I only really recommend that for very, very large images. So I'm going to use no compression. The frame rate, you kind of have to work out yourself. Now this is 30, because it's 360 degrees and 10-degree increments, this has created 36 images. Now, if I want this image, this movie to go for, say, 10 seconds, then 36 divided by 10 would be 3.6 frames per second. But I'm actually going to say I want this movie to go for 6 seconds, which is 36 divided by 6 seconds is 6 frames per second. So if I click OK, it's going to ask me where do I want to save it, and I'm going to click. I'm just going to save it in our shared folder. So now that's already done. So now if I go back to our shared folder, which I now need to find again. FIJI resources, it should now be in here. So if I double click on our projection there, it'll open up our media player, which is there. So now you'll see that I have a 6-second movie of my rotation data, and then you can put that in your PowerPoints, etc. If you want more of a free play 3D viewer, you can use the free volume viewer in the plugin folder. So this is my raw data again. So if I go into plugins and use the 3D viewer, give it a second. It asks, I usually leave this as default. You don't really need to change anything, and just click OK. And then that's gone over to the other window again. You get this. So I'm going to use I'm using my wheel on my mouse. Now, if I left click, I can then drag this to view the 3D. And then you can zoom in and zoom out and stuff like that. Now, you can actually create a video by setting what's called landmarks or landmarks within this. So you'd set a landmark there, set a landmark there, set a landmark there, and then you would press record. And actually, I'll do that very quickly. So if I add, now where is it? And no, where is it? Where is it? Lost it. I'll go over that at a different time. I might go over that in part 2 because I've completely forgotten how to add it. But essentially what you would do is you would add different positions and then you would click record, and then the software would then move to the shortest distance between those points and create you a recordable video that you can then put in your presentations. It's saving the 3D viewer, which leads me to basic analysis. And whoa, we're bang on time, 2:50, perfect. Okay, so measuring is usually one of the main reasons that people would want to use ImageJ. Now you can use use ImageJ to get quantitative data in the form of areas and intensities and pretty much most values that you would like. So it's very, very simple to do measurements in ImageJ. However, the first thing you need to do is tell ImageJ which measurements you actually want to measure, which values you actually want to measure. So you would go into Analyze and click Set Measurement. So this brings up the Set Measurement window, which I've now lost there. And there's a whole list of things that you can actually measure. You know, area, standard deviation of any of these values, min and max gray values, integrated density. Integrated density is total intensity. So you've got mean gray value, which is the mean intensity, and you've got integrated density, which is the total density. Area fraction, we'll talk about that in a second when we do thresholding. Perimeters around ROIs, centroids within ROIs, spheric's diameter, which is the shortest distance within an object, and lots of different things. So I'm going to set area, mean gray value, and area fraction as a start point. I'm also going to click limit to threshold, which I'll show you why in a minute, and display label. Display label displays the name of the image in the results table. So it's very important. So I click OK. Okay, so what we're going to do is we're going to open an image. Let's open up the cytoskeleton green. So hopefully the recent image is working again. Yeah, honestly, I think that's broken. The recent image is not working for whatever reason. Anyway, let's just open that up manually. Here, FIJI resources, part 1. And I'm just going to open up cytoskeleton green. Here we go. And it's popped up there. So you can literally just click the measure button. If you click measure button, it will give you a results table. It gives me the label, cytoskeleton green. It gives me the area of the whole image. It gives me the mean intensity of all of the pixels in here. Of course, we've measured 100% of the area, and it also shows me the threshold. Now, we haven't really talked about thresholds yet. We'll get into that soon, but it shows me that I'm thresholding the entirety of the data. So from 0, I'm including 0 to the maximum, which is a 16-bit image. So 2 to the power of 16 is 65,535 gray levels. So that's my measurement there. Now that's fine, but I'm measuring the entirety of this. Now I may want to measure only a part of it, which is where my ROIs come in. So I can select maybe the square tool, and I may only want to measure this part of it. So I'm going to select that, make sure it's highlighted, so you can actually see it's highlighted there, and then I'm going to click measure again. Now, you can either click measure by going to analyze M, or analyze measure, or just click the M button, and measure will automatically measure it. Now you can see that the area is smaller, and because instead of measuring the whole thing with all of the background blacks, black pixels, the mean intensity is actually increased because I'm only measuring cells. And you can do that with any ROI that you want. You can use a manual freehand, press M, and that will give you a different value. You can, of course, add these all to the ROI menu. So if I want to, ROI manager, I should say. So I'm going to add a whole bunch of ROIs to this. And from here, so if I close the results, it will delete those. So if I go here and measure this, so instead of going to measure here, I'm going to select my ROI and click measure there, and that will measure just that ROI. And you can actually see the name of the ROI there. I can rename that if I wanted to. So cell area 1, and okay. And so when I measure it again, cell area 1. And then I can go through and do that with all of that, measure, and I get different measurements. Or I can actually highlight the ones that I want to do, and I can go to multi-measure, which is in the expanded menu, which is down the bottom, and choose, where's multi-measure gone? Multi-measure, there. And it will, 1 row per slice. No, I don't want 1 row per slice because I've got 1 single slice and I don't want all my results to be in the same row. So if I click OK, we now get all 3 of those measured. So if I do that again, I'll close that results window, multi-measure, and all of the results are automatically measured. ROI Manager, measuring using thresholds. So measuring using thresholds allows me to filter out and select specific pixel values in order to measure just those pixel values. And it comes in really handy with especially fluorescent images. So the threshold tool, you'll find under Image Adjust Threshold. However, I just use Control-Shift-T to select that very simply. Oh, how do I do that? Okay. So if I can click Control-Shift-T, automatically the image turns red. And that's because it will automatically default to the default threshold. It'll try to do it itself. So just like we did with the brightness and contrast controls, you can use these controls to select more or less of the pixel value. So if I want to only select the very bright ones, I would select this area. If I wanted only the dark pixels, so for example, the background, I can use just this area. So all of the pixel values between 0 and 6941 are selected and ready for analysis. So now if I wanted to analyze and measure the background, all I would do is now click M, and I've lost my measurement tool. There we go. So now only the value within this image based on the threshold has been selected. And you can actually see that 36% of the image has been analyzed. So that means that the background takes up 36% of the image. If I do the opposite and I select just the cells and skip the background, and again I click Control M, it says that 60% of the data measured is cells, and you can see the difference between the background and the mean intensity of the background versus the cells. The cells are obviously a lot brighter versus the mean intensity of the background. So you can get you can isolate that very easily, and you can combine it with an ROI to only select a certain part of the image, which is also thresholded. So if I go measure, now we're getting a very small part. The area is only 37.623 pixels, and the intensity is this much. And now it's doing the percentage area of the ROI, not the whole image. So 71% of the ROI has been thresholded to the cells. So you can get that data pretty simply. So that's a very, very basic analysis. So you can do sort of analysis with intensities and areas and thresholding and ROIs and things like that. I will be expanding this significantly in the part 2, which will be in May, which will involve us doing a lot more automated analysis. So this is automated particle counting. So if you want to count cells without you having to do this, for example. So you can, if you really wanted to, you can manually count objects. So if I bring up, I go into the data drive, FIJI workshop resources, and if you get blood 60 times, now this image is actually a it's a blood smear from a friend of mine, and she has a disease known as thalassemia, which causes some of her red blood cells to actually turn into these little sort of flowery looking morphologies. Now, if you wanted to, you could then use the point tool to then go through and count the number of abnormal cells like that. But there are ways of doing this in automated functions. And then if I go measure and I bring up my results, it'll actually show me that I have 1, 2, 3, 4 cells that I've counted with that. So you can use, and if you look really carefully at the actual points, you should actually see the number of points that you've actually got. So 1 is 4, 4. So that was the last one I did, and you can see the 4 that's there. So that's what we'll be doing more in, it'll mostly be in it won't be really in the bright field space, but it'll be more in the fluorescent space. So automating your analysis. So we'll go over a quick refresher, very quick, of what we've gone over in this part. Then we'll be looking at automated analysis. So if we wanted to do automated particle counting, and I'll just do one very, very quickly. So for example, if I bring up nucleus blue from our three channel. Now, if I did a quick threshold and I thresholded out my cells there, and then I went into what's known as the analyze particle function and set up a bunch of filters, we'll be going over this more in depth. Then I could then use this to automatically count all of these cells. So if I click OK on this after filling in the correct functions, you can actually see I've left a few ROIs left over, but you can actually see these from the last analysis. There we go. So you actually see that the particle counter has automatically counted all my objects in about 2 seconds. So we'll be going over more, letting FIJI do the work for us rather than us having to do it manually. We'll also be going over image optimization. So this will involve color deconvolution, so separating out channels like for H&Es and HDAB. If you want to separate out the DAB channel from your hematoxylin channel, we'll be doing that. Stack alignment. So if you have an image stack, and I'll bring up an example very quickly. Part 2, where is it? Image alignment. Here's a great example, which we'll be going over. So if you have an image like this is from the old Star Trek show, and this is when they're being attacked and they're being thrown all over the place. What we'll do is we'll be stabilizing that image. So essentially, it won't move. Everyone will be throwing themselves all over the place, but we'll essentially steady the camera to be not moving at all. So that will be stack alignment. Extended focal imaging, we'll be using Z stacks, not exactly how we were using with the maximum projection, but bright field imaging. So using extended focal imaging to essentially take an image like this and remove the blurry parts of it and merge together only the in-focus parts of it to create a completely in-focus image. So that'll be extended focal imaging. Tile stitching, if you have multiple tile scans, for example, this brain here. So if we have basically take multiple images, we can then use ImageJ to stitch it together automatically. Now, this is only 4 images, but basically the sky's the limit. We can do as many as you need to, as long as you've got overlay. So you can actually see the overlay there. It can recognize that there is an overlay there and stitch it together into a single image. The display. And then we'll be looking at artifact correction. So you will remember our image from, if I bring it up, the stage micrometer, which I'd like to say I purposefully took purposefully acquired that to look terrible, but it was purely by accident. So you see with this image, you've got a lot of what's called vignetting around the edges. Now this sort of dark area, so we'll be removing things like that, and removing sort of spots and things like that in a way that makes a lot of sense and isn't manipulation in a bad way. We're correcting things, say if there were spots on the camera, not necessarily your image. And then we'll be having a chat about the next session, so part 3, and potentially looking at some macro programming, so the basics of macro programming before the one in November. So that is all I have to say. So thank you for sitting through that for 2 hours or just over 2 hours. I'm actually surprised I managed to. It's the first time I've actually run through it completely in the new format, but I've hit the time pretty well. So if you've got any questions to ask at the very end of this, please feel free to turn off your mic and ask me. Otherwise, if you're sick of listening to me for now, feel free to email me with any questions that you might have. If you have any programming, any script writing that you would like to do, if you have some analysis problems that you would like to try and solve, drop me a line. Or if you want to sort of try and automate it with a script, I'm always happy to help. So I will leave it at that. And I will see you hopefully at part 2. I'll send everyone a calendar invite once I get the date for that, and invite you all to the second part. So I will leave it at that, and I will see you later.